all of the great history that we've heard about by Xavier Le Pichon and Carlo Leitgets before took place when I was a kid. So I knew nothing about it. But as our convener just said, I came across it at school. I was lucky to have a geography teacher who inspired me and a physics teacher who thought that going into earth sciences was just the right thing for me. I think they had a good choice there, making me do it. And although this was in the late 60s, they already knew about plate tectonics. When I went through my education at university, they knew about plate tectonics, but they didn't really think it was the appropriate idea for earth sciences. So I was trained rather in a conservative environment. We were shown as students images in earlier stages such as these, suggesting that this was just one of many hypotheses that could explain the way that our planet works. In fact, most of my university professors preferred the idea of contracting, of a contracting Earth that was gradually shrinking like a drying apple. Today we know this to be nonsense, but in fact this in the late 70s was still one of the things that happened. One of the things that inspired and fascinated us as young students was also an important asset that we now know to be one of the key aspects in plate tectonics, and that is the fact that earthquakes as well as volcanoes are systematically distributed along or across our planet and are virtually nearly always related to the boundaries of our plates. And this was one of the earlier observations in the plate tectonics communities already in the 60s, and likely earlier if you look at the work of Benioff and Vardati. But the key point here is that it is the nature of plate tectonics as a kind of unifying theory that we as young students really considered to be something of real beauty. A unifying theory is something that in the history of science you can always find as a core element providing something like a fundamental new breakthrough in the understanding of whatever process you are analyzing. Now, this is not just fascinating because of this distribution that I'm showing here. It's also fascinating because of this, the way that we humans settled this planet. And there's an intriguing relationship with most megacities being formed at those places of our planet where it's most dangerous. Very likely, this is not due to the fact of there being risk, but also due to the fact that there being resources. And the unifying theory idea is also supported by this aspect that a number of key geological processes are controlled by the plate tectonics machinery. In the days when I was educated in the second half of the 70s and also in the decades following that, one of the big debates in the plate tectonics community was still raging about the forces that was driving the system. We were struggling whether convection was really a two-layer or single-layer, which kind of forces were really driving the system, whether it was the push of the gravitational push of the ridges or the gravitational drag of the down-going slabs. Whatever it was, this debate has subsided to some point, but there is still some discussion up. And the numerical model here practically reflects our current stage of knowledge, showing that there is an intricate coupling, as we've heard before, from the plates floating on the weak subsurface and the mantle involved in the convection scheme. But this is not what I want to talk about in the following. We've heard some of the history, and we'll see more about that likely during this course. What fascinates me and what I thought was the appropriate perspective of looking at it, why the heck is our planet plate tectonic and the other planets are not? This is a fascinating question, not just because they're fairly similar in size, a little difference here and there. They are also fairly similar compositionally. So why would they exhibit different styles of the way they function? And this is something that will be passing along as a red line through what I want to show to you. It is really a history or a story of interactions and feedbacks that are providing a very complicated machinery, but this machinery ultimately does something that makes our planet look distinct from the other silicate planets that we have in our solar system. So let me start by looking at some of the first order constraints or requirements that we need to have on this planet to allow it to be a plate tectonic one. One that is very obvious, it needs stiff and rigid lithospheric plates. And given the temperature that we have at the Earth's surface, which round about the globe, the average temperature is about 20 degrees C, we get this kind of strength development with depth. The plates with depth become stronger, and then at some depth, they switch to another deformation mechanism. The silicate minerals that our planet is composed of become weak. So this part constitutes the stiff parts of our planet that are able to float on the underlying mantle. And in fact, if you look at it through the thermal argument, again, you have the near-surface lithosphere temperature, which is just about 20 degrees C, and as it goes down, it straddles the melting limit of solid rock. And this is what makes the substratum of these plates weak or movable. So they're virtually moving on this weak layer. This is something that we have known for a while. But this is important because it provides a first-order contrast if you compare it, for example, to Venus. The surface temperature is in excess of 400 degrees C. So the rocks at the surface are as weak as pudding. There's no way they can have plates because it's simply too hot. Another aspect is if you want to move around plates, you have to move them past each other on the faults that bound the plates. And if these faults are as strong as the plates are and as stiff as I've just shown you, plate tectonics would simply be impossible. So the interesting question emerges, what makes these faults, the boundaries between the plates along which they move, just about strong enough that you can have earthquakes as suggested here, with stress being loaded and unloaded and released during earthquakes, but weak enough such that they can move and not get stuck. There's one very fundamental aspect that I need to introduce you and come back to. I was mentioning this just before. The strength of our plates increases towards depth, and it does so with a gradient that we call the coefficient of friction. You can just rub your hands and you are feeling your personal coefficient of friction virtually generating a lot of heat. And if you lubricate that or if you weaken it, as for example shown here, you're making it weaker than the plates on both sides of it. And that is a fundamental pre-requirement. Otherwise, you will not be able to slip these faults one past the other. So one very efficient way, and it's very probably the most efficient way that we know of on this planet, is to do it with water. You know all yourself the effect that if you lubricate your hands with water or soap, they will slide like nothing, without any resistance. The same is what is happening in rocks. Once you have fluid in them and the fluid is under a pressure that is high enough, it will squeeze the grains and fractures apart and make the rock weak, as shown here. And in fact, this leads to the situation that the coefficients of frictions on these faults that have fluids in them can become excessively weak. This allows them to float, to nearly float or to produce something that is something very akin to whatever you have experienced if you once experienced aquaplaning. Physics is the same. Interestingly also, if you can compare that in numbers, it's the same as a banana peel. This was even rewarded with an Ig Nobel Award a few years back. So you could consider plate tectonics on this planet to only be possible if the boundaries between the plates are as weak as banana peels. Otherwise, plate tectonics would not be working. This is a fundamental aspect that we are gradually beginning to see. And we're beginning to see that it's not just the cool temperature at the surface that is required, but there has to be free water. Plate tectonics is virtually only possible on a hydrous planet. On a dry planet, it would be impossible. And the water has to be on the surface, not like in Venus in the atmosphere, where it has all evaporated due to the heat. So we have seen that plates have been moving around and in a very complicated way, as shown here by this animation, that we at the present day can virtually measure using GPS methodology, and we'll be hearing more about that, I presume, tomorrow by Chris Vigny. But what I want to focus on in the next few minutes is here on the western margin of the system, where we have been doing some work in the past few years, looking at what happens at such a plate boundary and how does it operate and function. We have learned that it's extremely weak, that water is playing a key role, yet we also see that here we have an important mountain belt. It's the second biggest on this planet, the Andes. We can perceive why mountain belts would arise as a consequence or a direct consequence of plate tectonics, for example, by the collision that we've just seen here between the Indian plate and the Asian plate. Collision, that is very intuitive, produces strong deformation and crustal thickening. But why the heck would it do it at a convergent plate boundary as this one, where the Nazca plate or the oceanic plate is just moving into depth and the faults are so weak? How, in that case, do you produce mountain belts? That's an apparent paradox, but paradoxes are one of the most fascinating things in science, is driving a lot of our controversy and the research as well. So here we have a high-resolution topography of the Andes and the intervening oceanic plates, and it's virtually the opening of the South Atlantic that is driving South America to the west. We know this to happen. We can even reconstruct using the paleomagnetic evidence that was mentioned in the previous talk by Carlo Lai to really show with what velocities are we pushing one plate westwards. And we see that South America, over the past 120 million years, has been moving quite rapidly with a rate of 3 to 5 to 6 centimeters per year westward. And sometime around 60, 70 million years ago, it started slowing. And around 50 million years, it started slowing rapidly, and the Andes started rising. So somehow, for a long part of its history, South America had no problem in pushing the oceanic plate in front of it and nothing happening. And for some reason, around about this time, the oceanic plate stopped moving back and stood still, started standing still, and South America, that was still moving westward, simply had no other choice. It had to start piling up and deforming because it was meeting increasing resistance. So looking at it this way, we also need to look into the Earth, what may have been happening here that caused this. This here is the trace of the Nazca plate, which is the part of the Pacific plate that we have there, reaching deep into the mantle of our planet. And what you do see is not just the seismicity related to that, but you also see that it crosses an important boundary where it's changing its geometry and starting to spread out. So this is an important aspect that in recent years has been put some light into from experimental evidence looking at why is the upper mantle different from the lower mantle. It was known for quite a while that there is a minor change in the mineralogy, but not a massive one. But we now know also that there is a substantial change in the strength of the upper versus the lower mantle. And this has been shown by experimental work in diamond anvil cells. So this is when you squeeze very tiny minerals between diamonds that can sustain the very high pressures that you need to generate deep in the earth. And it was found out that, in fact, beneath the upper-lower mantle boundary, the viscosity or the resistance of the rock to deformation increases dramatically. So if that's what's happening, we think that it's in fact the penetration of the Nazca slab. We are now looking from the west, but as if we were a mole deep in the earth, would be seeing the Nazca slab plate hanging down. South America would be up here with the entire Andes. And you can see the Nazca Plate hanging down deep into the lower mantle, and this is the upper-lower mantle transition where the strength of the mantle changes dramatically. And in fact, if you map the onset of deformation of the Andes, as I mentioned previously, around 50 million years, and here it decreases to about 20 million years. And this is simply due to the fact that the Nazca slab, when it started hitting the lower mantle and penetrating it, it got rooted. It got virtually rooted in the lower mantle, and because its resistance to shearing or deformation is so much higher, pushing it away anymore simply wouldn't work. It got stuck. And this is what we currently believe is likely what is happening when the deep subduction reaches the lower mantle and material gets stuck there. It does not just pile up, it may penetrate, but it will get rooted, and any kind of pushing it back becomes more difficult. Now, the reason why I'm showing you this in particular is that it throws some light on how the surface of our planet is shaped by very deep properties. So that's an important feedback. It's the deep properties that have an important feedback on what our surface topography may be looking like, and on the fact that mountain building may in fact be controlled by one of these mechanisms. There's another one that is important. Again, the Andes looking from the central parts that are very high, the second highest mountain belt on this planet, to the southern one. And I've mentioned early on that these here started growing much later. But there's more of an intricate relationship. You can see that here, this is the extent of the Patagonian ice shield during the last glaciation. The white ones is the little that is left over from that last glaciation. But it's striking to note that this part of the Andes was glaciated. Now we're not looking into the deep mantle, we are looking up into the atmosphere. And what we see also that as a consequence of the glacial erosion that took place here, the trench offshore is completely filled with the erosional remnants of the southern Andes, completely filled. While here in the north, where it's dry and hyper-arid with the Atacama Desert, the second or the driest planet virtually, the driest desert on this planet, there's no sediment delivered into the trench. Here in the south, it's completely overfilled. And we also see that in the present day precipitation. Here in the south, it's really raining heavily. I can tell you, I've been there. Field work is not always pleasant. And there's a lot of material that is constantly flushed down into the Andes, into the trench, while up here in the north, it's absolutely dry. So we have an interesting natural lab that tells us how climate affects the growth of mountains, because we can directly compare it within one and the same origin. We can see, for example, in seismic sections what this transect is looking like. Bare of sediment, the broken and fragmented oceanic plate is entering the trench and going down. Here it is covered by 2 kilometers of sediment. Quite a lot of sediment that has been poured down from the southern Andes into the system in the recent history. We can even restore this over time, and we can see that for most of the last 50 million years, the trench in the south did not have any sediment either. It only happened about 6 million years ago. And that's when the glaciation started. So in fact, glaciation started the input of sediment here, and the sediment now is related to something that is quite interesting also when one looks at the tectonic history of the Andes. Here in the north, we can see that the Andes are actively shortening at a speed of a few millimeters per year. In the center of the Andes, we even go up to about 14 millimeters per year. The system is growing laterally. Here, in the southern Andes, with the onset of glaciation, deformation stops and dies. So what we think is happening here is that all the sediment that is piled up there, when it gets subducted into the subduction plate interface, it lubricates the plate interface, and we have another of these lubrication stories taking place. A lot of water-rich sediment is going down and weakening the plate interface to the point where there's no stress transfer of any relevance anymore between the upper and lower plate. So orogeny or mountain building is virtually stopped. So there's not just feedbacks, in fact, with the deep mantle, there's also feedbacks with climate evolution at the surface, shaping our planet's surface. Now, this is what I've shown, but there's an additional fascinating aspect if you compare this history to of the plate tectonic processes to what is happening with respect to the climate. This is illustrated here in this simple geograph, and what I want to particularly attract your attention to is this. This complex chemical formula tells you that our planet, that is a silicate planet, is reacting chemically with the atmosphere when it weathers. And it's in particular the mountain belts that weather because they have a lot of surface area and constantly there's fresh, unweathered rock brought up to the surface that can then react with the atmosphere. And you can see what the most important reaction for our purpose is the reaction with CO2. Because silicate minerals that are building our planet, when they react with the atmosphere, they remove CO2 and they produce carbonate. They produce carbonate, and the carbonate is stored on the shelves of the global oceans, thus very effectively removing CO2 from the atmosphere. And that is a very important aspect that I will show you in a minute, but before that, let me just illustrate that you can put the hands on these processes by just going into the Alps, for example. This is both are from Switzerland. This is in Switzerland, showing, in fact, massive carbonate deposits from a former marine origin, now high up in the mountains. There's a whole bunch of CO2 stored in these rocks. This is the Matterhorn, made of mafic silicate rocks. They are currently weathering away at a very high rate, as you can see here. Heavy weathering, virtually binding CO2 in the weathering products being removed to the present-day oceans. So in both cases, the storage can be seen, but also the active removal process. And what is happening here? The reaction, as all chemical reactions, is temperature dependent. So what happens as the climate warms, the reaction rate increases. And if the reaction rate increases, it will draw down CO2, so it will slow down itself. It virtually operates like a thermostat. If climate cools for some reason, for example, our planet going into an ice age, the reaction rate slows down and becomes sluggish, and CO2 removal from the atmosphere becomes too slow. So this is a fascinating aspect because this mechanism of CO2 weathering, in fact, is an extremely efficient mechanism maintaining fairly constant temperatures on this planet. Fairly, I should say, at geological terms, because it's a slow process. It only operates at a very long time scale, that is on the time scale of millions of years. But at this million years time scales, it's an extremely efficient mechanism of maintaining a fairly constant temperature. And it's particular the mountain belts that do the trick. This map here shows all the current mountain belts on this planet, not all of them, but most of them being active, so being actively uplifted, weathered, and eroded away. So they're constantly reacting away CO2 from the atmosphere. Now, summarizing this in this somewhat complicated diagram, one needs to look at the Earth history. We have a 4.5 billion year long history. And we have constant growth of continental material, but what is most striking to be seen here is what I was alluding to, the constant thermal conditions. This is the blue one, the ocean surface temperature over Earth history. You will see that it has been floating around 20 degrees C at the global average. Now this is striking for one important reason. Look at the heating by the sun. We know that the solar constant of our sun has been increasing steadily over the entire Earth history. So why the heck, would you ask, does our planet make it to maintain a constant surface temperature? Well, the only way he can do that, our planet, is by removing greenhouse gases from the atmosphere and changing the atmospheric conditions such that surface temperature is maintained at a fairly constant level. And remember that this constant temperature level was important for two aspects. First, we want to make sure that the lithospheric plates remain cold and stiff and rigid. And second, we want water to lubricate the plate interfaces so plate tectonics can work in the first place. So this is an important aspect that is a fairly fundamental property of our planet when we think about it in terms of plate tectonics. Because plate tectonics is playing a big role here. It is generating the surface area that can be weathered and eroded away. And this kind of thermostat that I was alluding to before obviously must be important in maintaining these rather constant surface temperatures. Unfortunately, there's no hope for this to help us away with global warming that we're looking forward to, because the process is simply too slow and sluggish. But over the long run of Earth's history, it's extremely efficient. I was still trained to believe that it's mainly the rise of the biosphere that was important in removing CO2 from the primeval atmosphere. But the growth of massive biosphere is much, much younger in history. So all of this has been happening over times when biosphere simply was not present to produce a substantial reduction in the greenhouse gases to the present day temperature regime. This was a constant, in fact, throughout our planet's history. Now, how does that feed in with plate tectonics? This raises another important debate that has been raging since the plate tectonics revolution, but it is still hot to this day and is currently even heating up. There are arguments that suggest that plate tectonics has been starting a long time ago, some 3 billion years, because we are getting more and more thick, differentiated, as we call it, continental crust, the kind of crust we are living on. Since erosion and weathering increases, the thickness of the continental crust starts decreasing again, the average continental crust. However, there's other important evidence, and that suggests that key ingredients that we consider typical of plate tectonics only started very recently in Earth history, so round about 800, 700,000 years ago. And these are in particular rocks that are direct indicators for oceanic crust to have formed. So the basaltic oceanic crust that we've heard in the earlier morning time would only be obviously present since about that time. The same is about high pressure rocks, so rocks that went down a subduction zone and for some reason made it back to the surface. Same age range. So we are left with a fundamental issue. Did plate tectonics really start as early as here, or did it only start in the present day style fairly recently in Earth history? And then what about this global thermostat that is keeping the Earth's atmosphere at a fairly constant level? Interestingly, so modern plate tectonics as we see it and perceive it today is a fairly young process, and so is the rapid evolution of multicellular life. It only started after that, and it is absolutely synchronous. Now, looking at the machinery of what makes our planet work, we know that the fuel is radiogenic decay. It is, in fact, a kind of nuclear reactor that has most of the heat engine from a radioactive decay deep in the Earth, but there's some residual energy from other sources. But this simple fact would tell you that over time, the motor behind the system should be slowing down. And how do we maintain plate tectonics going if the system is slowing? An interesting question that we yet have to solve, because some of the energy budget is not properly functioning. We know, again, looking at the entire Earth history, that the temperature in the deep mantle has been cooling to the present from much higher temperatures in the past. And if plate tectonics only started here, what was the kind of tectonic mode of our planet before? What we believe so far is that in the very early stage of Earth history, it was driven by what we call stagnant lid tectonics or single plate tectonics. So the entire planetary surface being composed by a single plate, and maybe some major episodes where the system became active because constant plume rise from depth would eventually cause the surface to break apart and to form very initial or early subduction. But overall, we are looking at a planet that is evolving in time, and for how long it will be able to maintain these very constant conditions that are required by the present mode of plate tectonics is an issue that we still need to solve. At least we can answer the question now that plate tectonics is definitely not an inevitable fate for any kind of silicate planet. In fact, we know just from looking out into space that other planets like Venus or like Mars are not doing it. They never got on the right path for a reason that is not easy to state. Our planet did, and we know that it's a vital aspect of the system's evolution to have gone through that stage, because it's unlikely, that is an important aspect that we are beginning to learn, it is unlikely that biological evolution would have worked as efficiently as it has done without plate tectonics. The important key aspect that plate tectonics provides the constant change of the Earth's surface, the constant change of biotopes, and the opportunities of new species to arise. So in fact, our planet being a plate tectonics controlled planet is extremely different, and it lives virtually on the feedbacks of these various components of the systems that stabilize its evolution in the scheme that I have tried to illustrate you via a series of complex feedbacks that provide and make it the complicated machinery it is. Now there's interesting other aspects that towards the end I would like to draw your attention to. We perceive our planetary surface as rock solid, virtually, standing on it. But just looking at this, we know that it's very sensitive to surprisingly small perturbations. We know that massive rainfall triggers earthquakes. Well documented in all these areas in the Swiss Alps that have a very good and detailed record about that. We know that drilling for these geothermal exploration wells triggered earthquakes by anthropogenic activity. The same happened during the deep drilling of the deep new alpine base tunnels. They also trigger earthquakes. And we know that the building of hydroelectric dams from the load of the water there triggers earthquakes. So the system we are progressively beginning to learn is in a very stable equilibrium. It responds to very small perturbations. We are beginning to perceive this as being a property of systems that we call self-organized critical systems that are able to respond to very small perturbations in ways that are very difficult to predict, because systems at such situations in the state become what we call scale invariant, and you lose the potential to really link causes to effects. The famous example being the butterfly on the southern hemisphere flapping its wings and causing a hurricane on the northern hemisphere. And in fact, it has even been suggested, this is a major controversy, that if you have a planet, a spherical planet with plates, in order to really do this geometrically correct, you have to do it like what every soccer ball player knows. You have to have a kind of coordination of plate numbers next to each other to completely fill the sphere. And it seems that the breakup of Gondwana, for example, a few hundred million years ago, seems to show this. This would again be a consequence of self-organized critical systems that organize their entire operation themselves. So what I've been trying to show you in a few minutes is that from the plate tectonics evolution 50 years ago to the present day, hot debates that we're having in the plate tectonics geodynamics community, we are beginning to learn that our planet is a system that we should not just look inside into the system. We need to understand its feedbacks, not only internally, but also with the atmosphere and how this changes. It's a silicate planet, but it has very characteristic chemical and mechanical properties. That is important. That would also be something that Venus and Mars share, but it's insufficient. We have a very limited temperature fluctuation with a fairly stable radiogenic heat source, but that is gradually running out. Estimates are that we have enough energy left there for about 500 million years of plate tectonics of the current style, so nothing for us to worry about. But it's interesting to note that the fate of any such plate tectonics planet is not forever. We have all these negative and positive feedbacks that are stabilizing these thermal boundary conditions internally and at the surface. That is important because it seems that this is a fundamental requirement to allow the system to operate in the mode that we are in currently. And finally, it looks like there is some properties of self-organization in these system components that are able to maintain one of potentially several stable tectonic regimes. There's not only one, as you've seen. Other planets have a single lid kind of plate tectonics. So there's more stable regimes out there that are being run by various planets in our universe. Thanks for your attention.